Hello, everyone, and welcome to the Summer Space Academy. My name is Maya, and I'm a communication officer at the Luxembourg Space Agency. I'm very happy to host today's webinar with you. Thank you all for joining the very first webinar of the Summer Space Academy. Before we start, just a quick note that this webinar will be recorded and it will be published afterwards on the Luxembourg Space Agency YouTube channel. So you can always rewatch it or share it with your network. This webinar is part of a series organized in the context of the Astronaut for a Day contest. The idea is to give you all the opportunity to learn more about the space sector, its opportunities, and the people working in it. For those who may not be familiar, Astronaut for a Day is a unique contest taking place this year in Luxembourg, Austria, and Estonia. A group of finalists will be selected as space ambassadors, and I think some of them are already in this meeting. And they will take part in an incredible experience, which is a parabolic flight, which will take place on October 15th, departing from Luxembourg. Afterward, they will represent the program as space ambassadors for 1 year. This first webinar is organized by the Luxembourg Space Agency, also known as LSA. And to give you a bit more information about what we do, so our mission is to develop the Luxembourg space ecosystem. We support innovation, we provide funding, we provide technical means and access to research, and we connect with international partners and maintain those partnerships. Through initiatives like the Summer Space Academy and Astronaut for a Day, we want to inspire young people and encourage curiosity about space and science. Regarding the webinar today, here is how it will run. So I'll start with this short introduction, which is not short anymore. Then we'll move on to our guest speaker's presentation. And after that, we'll give some time for questions and answers if there are any. And finally, I'll wrap up with a brief conclusion. Now, it's my pleasure to introduce today's speakers. Timon Schild. Timon is a 29-year-old Swiss and French national. He's currently finishing his PhD at ESRIC, the European Space Resources Innovation Centre based in Luxembourg. But I won't give too many details because I think he's going to introduce himself and talk more about his background in a minute. So let's get started. And Timon, the floor is yours.
Hello, everyone. Thank you, Maya, for the introduction. First of all, can you hear me okay? Okay. I'm going to start sharing my slides. If you could just quickly tell me. I can't see the Teams anymore, so if you can just quickly tell me if the slides are okay.
Yes. Yeah, we can see your slides. That's all good.
Okay, perfect. Thank you very much. Well, as introduced, I'm going to give you a quick introduction presentation on the topic of space resources, which is a very broad topic. So it is going to be an overview of the topic in itself and of all the activities that are going on in Luxembourg at the moment on this. This is going to be 30 to 40 minutes presentation. I'll try to keep it reasonably short so that we have a bit of time at the end for questions and discussion. Okay, so what are we going to talk about in this presentation? So first of all, I'm going to talk a little bit about myself, about who I am and how I ended up working in this domain in space resources. Then we're going to define what space resources are. We're going to ask ourselves why we are interested in them in the first place. And I'm going to give a quick example on how we could use space resources. And finally, I'm going to talk a bit more specifically about the Luxembourg ecosystem and what is currently going on in Luxembourg in the field of space resources. Okay, so who am I? So as introduced, I'm Timon. I'm 29 years old, Swiss and French national. I initially studied mechanical engineering, so nothing specific to aerospace. and I am currently working as a PhD candidate. So I'm in the final year of my PhD studies at ESRIC in Luxembourg, together with the University of Luxembourg. And my research topic is space resources in general, but more specifically, the production of oxygen and of metals on the moon using the minerals we can find on the moon. I'm going to talk, of course, a bit more about this and about what this means. So how I ended up getting here. So as I said, first of all, my study background is mechanical engineering. So I attended 2 universities. So I spent 6 years in total, 4 of which at INSA Lyon in France, which is their generic engineering school. And as part of a partnership, I spent 2 years at Trinity College Dublin in Ireland. And so those studies were just pretty general on mechanical engineering, but the first kind of contact I had with the space domain was through my master's project that I did during these studies, which was on CubeSats. So CubeSats, if you're not familiar, are small satellites, like shoebox size, typically 10 by 10 by 10 centimeters, and they're very popular for student projects because as far as satellites go, they are reasonably inexpensive to make. And so there are a lot of universities working on this. So this is kind of how I got with one of those CubeSat projects is how I got into the my feet, let's say, into space. But then I really got going through the opportunity I was giving for my first position, which was a national trainee program. So that's kind of a program for young graduates. I know Luxembourg is also running one of those in partnership with the European Space Agency. And so through this program, I got to spend 2 years at the European Astronaut Centre, which is a European Space Agency site located in Germany, in Cologne. And what I did there is I joined a team called Spaceship EAC, which hosts students and young professionals to work on different research and R&D projects. And there I had the chance to work on a variety of R&D projects on space exploration in general. So here you can see a few examples. For example, on the bottom left is a little project we worked on that was actually flown on the ISS. So it's kind of an analysis tool to analyze the eyes of the astronauts on the ISS. So we did space exploration in general, but more specifically, I started working on space resources. So what you can see on the top is different processes we're looking at to do manufacturing using what we call lunar regolith. So it's kind of the dust you could find on the moon. So how you could produce parts, for example, on the moon. So this is the kind of stuff I did there, and to continue in this direction once those 2 years is over, that is where I decided to join ESRIC. So I came here to Luxembourg, to ESRIC. I'm going to talk at the end of the presentation a bit more about who we are. And this is where I'm currently, and I'm doing research, so a lot of lab-based work on a specific process, as I said, to extract oxygen from rocks on the moon. And then, of course, part of the research work is also communicating those results to different audiences, for example. So that's hence why I'm here today. So enough about myself. Let's dive a bit more into what's actually at hand, which is space resources. So what exactly do I mean when I talk about space resources? So a very broad definition of space resources is, well, it needs to be in space, otherwise it wouldn't be called space resource, and it needs to be something useful because it's a resource. So you can define a space resource as anything that is useful that you can find in space, but that encompasses a lot of things. Here are a few examples. So classically, when you talk about resources, you very quickly talk about resources as we know them on Earth. So natural resources, what I will call extractable resources. Throughout the solar system, you can find rocks, minerals, you can find water and other liquids. You can find different gases. So for example, the oxygen we want to produce, CO2, methane, those kind of things. You can find metals as you find metals on Earth. So all of those natural resources that you could extract and process to use. A more intangible space resource, but actually one which is the one we already use the most, is energy. So when you are in space, in all the places you have sunlight, you can produce energy locally. So that is a form of space resources, and that's how all the satellites that are currently flying in space, or 99% of the satellites, produce their energy. They have solar panels. When you are not floating around in space, but you are on a planet, for example, you can also use temperature differences between hot and cold areas to produce energy. So that is also a form of resource, something useful you find in space. The next category is the environment. So it's not necessarily something you extract, but something that is just there that you can use kind of passively. A very good example is the vacuum. There are some cases, for example, when you're doing experiments or you're doing some processing, where, for example, having vacuum is really, really useful. And in space, well, you have infinite vacuum available, so that can become a resource. Also, reduced gravity. When you're floating around in space or when you're on the moon, you experiment different gravity levels, which can be, in some case, useful for what you want to do. Another one which can be considered a space resource is stuff that we are actually bringing or that we brought in the past that we can recover. So things we can reuse and recycle. For example, we already have spacecrafts that we've flown to space that are no longer used, but we could actually recover them and use the materials that they contain. It is a resource that is currently in space. Another example is organic waste. As soon as you start flying astronauts, you will have the waste from the astronauts, you will have food waste, etc., that you can try to recycle and use as something useful. And the final one I'm going to mention here is the location. So depending on where you are, for example, if you're on the moon, a specific location can be a resource. If you find a cave, it can be something you can use to protect yourself, for example, from the sunlight, from the radiation, etc. So all of this to say that space resources, although in most cases we will see it as this first category, which is natural resources that you can extract, it covers a super broad range of topics. To narrow it down a bit more, what is interesting to look at is the destinations, is where are we going in priority for space exploration, and so where are we going to need those space resources? Well, the three current main targets for exploration are the moon, Mars, and asteroids. So if you look at the moon, what you can find there, for example, is you can find minerals. The different rocks you have on the moon are a resource. You can find in very specific locations, the polar regions, you can find small quantities of water ice, which could be very valuable if you have astronauts, for example. You can also find some traces of different volatiles that have specific applications, for example, helium. Mars is pretty similar. The two main differences is, first of all, it has an atmosphere, so you can actually recover CO2, which you can turn into oxygen, for example, from the atmosphere, which has already been done. There has been a small experiment on a rover on Mars that has been able to produce oxygen on Mars using what is available on Mars. And you also have a large amount of water on Mars. So you have those, you can actually see them on the picture, those ice caps. And in the depending on the season, you can have ice at a large range of latitudes. So you can have access to water when you are on Mars and know where to look for it. And the last one, asteroids. Asteroids are more diverse. There's different types of asteroids, but generally some interesting things you can find other than what we've already mentioned is metals. There are some asteroids called metal types that are actually mostly made of metals, so you can directly recover metals. And there are also some asteroid C types that contain carbon, which notably, for example, on the moon, we have very little amounts of carbon. So this kind of gives you an idea of what we want to recover where. Of course, as I said, I'm not going to have time to cover all of those. It's mostly to give you pointers if you're interested in the topic, what you can look at. But now I want to address one of the key questions that often gets asked and that we should rightfully ask ourselves is, why are we interested in those space resources in the first place? And for that, I'm going to have a quick look at the past, which is Apollo. So you may be familiar with the Apollo program, which is when over 50 years ago, we sent humans to the lunar surface. We often talk about Apollo 11, which was the big day. It was the first time we went to the moon. But I want to talk a bit more specifically about Apollo 17. So Apollo 17 was the last of the Apollo missions, where we sent, as all other Apollo missions, 3 astronauts around the moon, and 2 of which landed on the moon. And this was the largest Apollo mission, the longest one. And we spent a grand total of 3 days, 75 hours on the lunar surface. And of those 75 hours, we actually spent only 22 hours outside of the spacecraft actually doing activities on the lunar surface. From those 3 days, what we brought back were about 100 kilograms of rocks and samples for analysis on Earth. So I don't want to play this down like this is this was an enormous achievement, the Apollo program. But if you look at the figures like this, in the end, on the biggest mission from this era, we spent 3 days on the moon. And to spend those 3 days on the moon, we had to use one of the largest rockets that we have ever built. So that was the Saturn V rocket that was used for the Apollo program. It's 110 meters or 111 meters in height. That's basically a flying skyscraper. It has a mass when it's not filled, so the structure is around 200 tons, and it is filled with over 2,600 tons of propellant, so of fuel and of oxygen to make the rocket fly. Of this whole stack, of this massive piece of equipment that we sent to space, what came back with the astronauts inside and the 100 kilograms of rocks was this tiny part at the top, the capsule. So less than 6 tons came actually back to Earth. Everything else was spent in the process. Everything else was either while flying up, ditched in the ocean, ditched into space, used up, all the fuel was used up, and we only came back with this. So with the largest rocket we've ever built, we've been able to do a 3-day mission and managed to bring back the 3 astronauts safely with 100 kilograms of rock. So basically what that means is if we want to go further, either with longer duration missions or we want to go to different destinations, if we want to have a permanent presence, for example, on the moon, or not even permanent, if we want to be able to stay for weeks or months at a time on the moon, we can't bring everything from Earth because we would need tens and hundreds of those rockets. What this means is that we need to maximize what we can use, what we can find there. So for example, if we want to build a lunar base, which is the picture on the right, you will not bring all the materials to build them. You will use the materials that you have actually there. And that's kind of one of the core principles of space resources. And why this is important is that it is a necessity in order to make longer duration missions possible and in order to go further into the solar system, because that's the moon. The moon is kind of in our neighborhood. It's the closest thing. If we talk about going to Mars, this problem basically becomes even worse. So that's, in my view, the main argument for space resources is you don't want to bring everything you need with you. You need to be able to use what you can find there. So now that we've a good idea of what space resources are and how or why we need them, I'm going to give a quick example of what the use of space resources can look like and what we can do with them. So the example I'm going to use is a specific mineral that's called ilmenite. So ilmenite, it's an example of mineral that you can find on the moon. It's also a mineral that you find on Earth. And chemically, the definition of ilmenite is it's an oxide of iron and titanium. So it contains iron, titanium, and oxygen, as you can see on the formula here at the bottom of the screen. The thing we're going to be interested in here is the oxygen content. So you can actually use it to produce oxygen on the moon. And oxygen is very important because you can use it, first of all, for your astronauts to breathe. You can also use it as part of the fuel for your rockets. So you can refuel your rockets when you're on the moon, and hence you need to bring less things from Earth. So how do you do that? So here, this is a bit of a complex slide. It's the most technical one I have here. So this is an example of the process that we call reduction by hydrogen that can be used to extract the oxygen from iron oxide, so from ilmenite. So bear with me for a second while I talk you through this. So the idea is you put your ilmenite in a sealed container, and then you flow hydrogen gas into it. And what happens is this massive reaction here at the bottom of the screen. So first of all, the hydrogen that you are bringing with you is going to react with the ilmenite that you found on the moon to produce water, and also as a secondary product, iron and titanium. So you're basically stripping the oxygen off the ilmenite to produce water. And then what you can do with this water is you can feed it into an electrolyzer, which is a technology that is well known, that we know on Earth, that can be used to split this water into hydrogen, which you can put back into your system. So you're not losing any of the hydrogen you had to bring. You can reuse it over and over and over. And what you get in addition is the oxygen that you have been able to extract from your ilmenite. So there are many different chemical reactions or electrochemical reactions or different extraction techniques that we are looking at similar to this to basically take minerals or any other resources you may find on the moon, on Mars, etc., and process it in order to extract something that we deem valuable. In this case, for example, it is the oxygen. But this extraction, and this is kind of one of the core messages about the development of space resources in general, this extraction process, it is often a focus point. So developing those chemical equations, developing those reactors where you can put in a resource, you can put in a mineral, and you get out your oxygen or your water or whatever you're interested in. But it's actually part of a much broader chain of processes. So before you're able to extract something, the first thing you'll have to do is called prospecting. First of all, you need to, for example, in the case of ilmenite, well, you need to find out when you are on the moon, where can I find ilmenite? Because you don't find it everywhere. It depends on the location. So you need to do satellite imagery, you need to do reconnaissance in order to know where you can find your resource. The next step from there is, okay, you know where the resource is, then you need to dig, you need to extract it, excavate it, and you need to transport it. So there's kind of this mining aspect of space resources that we don't like to talk about space mining because mining has can have a negative connotation, but it is actually essentially what it is. You need to get the stuff from where it is. Then you have what is called beneficiation, which is, well, if I take a shovel of ground or of rocks on the moon, it's going to contain a lot of different stuff. We do beneficiation, which is basically the separation of the different elements in there. So if I have a pile of rock, I only want to keep the ilmenite, which is the mineral I'm interested in, that I can then use for my process. So this is all of those are very important steps that need to happen before you can do your actual extraction stage, your oxygen production stage. And then on the backside, you have all the post-processing. So, okay, you are getting water, you are getting oxygen out, but this oxygen is also going to contain impurities. So you always will need to have a purification step to make sure that the oxygen is of good quality. Storage is also an important step because you can't just produce it and then let it go anywhere. You need to store it properly in order to be able also to deliver it to a final client. And the final important step is also the waste management, is all the things that you did not use in the end, or all the secondary products, you also need a way to use them, especially because you are in a place where resources, albeit are very precious and limited. So what you want to do is get the most out of it, of course. So maybe this is all a bit theoretical, but the key message is the exploitation of space resources has to be considered as a full chain of processes and not just one single process. And all of those steps, basically, I mean, for example, my PhD, I'm working on one specific little fraction of this extraction box, but you can have many PhDs on all of those different boxes. So there is a real need to work on all of those steps individually and then as a whole chain in order to get to the use of space resources. Okay, this was maybe all a bit heavy and theoretical. So now, what are we doing day to day? What is actually happening, and specifically what is actually happening in Luxembourg at the moment to make this use of space resources a reality? So here, this final part of the presentation, it's mostly going to be an overview of what is going on and really basically some keywords and some topics you can look into further in detail. But so the starting point of this whole thing and the kind of overarching framework is the spaceresources.lu initiative, which is an initiative that was started in Luxembourg by the Luxembourgish government in 2016 to address kind of all the aspects of space resources. And it includes 5 main pillars, which I've outlined here. So you have legal aspect. So legally, how does the use of space resources work? What's the framework for this? International cooperation is a very important aspect. Technology and business development, together with research and education, to kind of push the technologies and the knowledge we need to do space resources. And finally, the funding and instruments. How do you allow the researchers, the investors, the businesses to work on those topics? So yeah, I'm going to give a few examples of all of those. So first of all, the legal framework. A concrete action that was taken is Luxembourg is the first European country that has an actual law on the use of space resources. So in Luxembourg, you can actually contact, if you are a company, contact the Luxembourgish government and ask them for a framework, for a permit, basically, to go to space and extract space resources. So it kind of provides some level of certainty to whoever wants to invest in this domain. International cooperation is something I mentioned as well. Luxembourg is one of the original 8 countries that signed the Artemis Accords in 2020. So Artemis, it's kind of the spiritual successor to the Apollo program. So it's the current program led by NASA together with all of those international partners to bring astronauts back to the moon and to make longer duration missions to the moon. And Luxembourg, at the very beginning of the Artemis Accords, Luxembourg was a part of this initiative. Business is a very important topic as well. Here, this is taken directly from the Luxembourg Space Agency. There is a growing network of different businesses and academic actors and public actors that work on space in general and on space resources specifically in Luxembourg. So here is a quick link to a directory that basically lists all the actors in Luxembourg that are working in space. Going to the research and education side, one of the evolutions in Luxembourg is that we have a new master's program at the University of Luxembourg dedicated to space technology and business. So it's a 2-year program that is held at the University of Luxembourg. It's of course there's registrations every year, so there is possibility in Luxembourg to get training for all of the opportunities listed above. So to work in the industry, to working at academia, there is now a framework to get there in Luxembourg. On the research side, one of the big events that is happening every year in Luxembourg, if you have the chance maybe to have a look at this, to attend it. I know every year we have some students coming. It's the Space Resources Week. So the Space Resources Week is actually the largest international conference dedicated to space resources that happens every year in Luxembourg. So this year's edition, for example, was in Kirchberg. We had over 450 people attending from all over the world. There's about more than 140 people actually presenting their work, and it's a great place for all of the people mentioned above that work in space and in space resources to communicate what they're doing and to find avenues to collaborate together. And then finally, as we say, last but certainly not least, ESRIC. So where I currently work is also an integral part of this ecosystem in Luxembourg. So it's the first research and innovation center that's entirely dedicated to space resources. So ESRIC, it was created again as part of this overarching spaceresources.lu initiative in 2020. We are located in Esch-sur-Alzette, where we currently have 27 people working on different aspects of space resources. We are hosted by LIST, the Luxembourg Institute for Science and Technology. We are part of this institution, and we have very strong partnerships with the European Space Agency and the Luxembourg Space Agency, of course. What we do research. So, for example, the process I showed earlier, this one of those ways to produce oxygen on the moon, we have setups, we have experiments, reactors in the lab that we are testing to figure out how they work, how they can be improved, how they can be adapted to work on the moon, etc., etc. We also work with businesses, so we have a program to help startups set up their business on space resources in Luxembourg, and also a business acceleration program for more established companies to start specific activities on space resources. And finally, we also do community events and community building around the whole topic of space resources. For example, with events such as this one, with events like the Space Resources Week that I mentioned earlier, which we are organizing. So we are a reasonably small team that's growing from year to year, and we are trying to address all the possible aspects of space resources that I have discussed throughout this presentation. So yeah, that is basically it from my side. I know this was a lot of information on quite a diverse range of topics, so I'm very happy to take any questions or discussions or comments you may have in the remaining time. And if something comes up later on, or if you want to get in contact, don't hesitate to reach out to me or reach out to the ESRIC team through the link that's provided here. Thank you very much.
I see there are some questions already in the chat, so maybe we can start with those questions.
Yes. Could you read them out to me? So
yeah, sure.
Yeah.
So from Stefan, hi Timon, does your research beyond oxygen also aim for the in situ production of carbon?
That's a good question. So in my case, because I'm looking at the moon, on the moon you don't really have massive sources of carbon. So I'm looking more at a process similar to what I was showing earlier, where you get oxygen and as a byproduct you may get metals, iron, titanium, aluminium, those things. The production of carbon, that would be when you look at ISRU, so space resources on Mars. Because on Mars, there has been an experiment, MOXIE, I believe it was called, that was doing exactly that. So it was using the CO2 that's present in the atmosphere and it was splitting it into carbon and oxygen. So there, when you're looking at more the Mars aspect of space source, you can have processes that produce carbon.
Okay. The next question is, are all ESRIC activities upstream in space? Are there any downstream Earth application initiatives?
That's a very good question. So currently most of our focus, of course, is getting to space, but the downstream application is very much an important argument in my opinion for all the activities we do in space, because there is always a legitimate question of why do you bother going to space at all? Well, one of the good reasons is that a lot of the technologies that we develop for space, we actually later find applications on Earth. One of my favorite examples for that is, WD-40, like the lubricant that you find in every hardware store all across the world. Well, that was initially developed for rockets, and then it became a staple product across the world. In our case, that's very much something we try to keep in mind as well, especially because what we're looking at is the use of resources and specifically the efficient use of resources. How can you, with a limited amount of hardware, produce meaningful products, extract meaningful products in a place where you don't necessarily have the ideal resources, where you basically are also constrained by what you have available. And that is also something that would be very useful to do on Earth, that we have a better use, a more efficient use of the resources we have on Earth. Maybe if I can continue on this, I'm going to give a very quick example. On the moon, one of the minerals that we're looking at to extract oxygen, which is called an orthosite, is a mineral that contains, among other things, aluminium. And actually, it's something that we could use on Earth to produce aluminium, but we're not necessarily doing it because we do aluminium production from bauxite, which is another mineral, and which is in a way better to produce aluminium, but then you need to have bauxite and you can't produce aluminium wherever you want. If we develop those technologies for the moon, well, maybe later on we can figure out that, oh, there is actually ways using those technologies that we can, for example, start producing aluminium in Europe. And so we don't rely on bauxite that comes from other places in the world. So that's the kind of downstream activities that we could be looking at.
Next question is, how much oxygen can you get from a certain amount of ilmenite?
That's a good question. So a lot, a surprising amount is the answer, because when you look at the kind of chemical formula, so iron titanium oxide, FeTiO3, 3 out of every 5 atoms you have in ilmenite is oxygen. And I don't have the exact figures for ilmenite. I need to calculate them, but for generic lunar soil, if you take a scoop of the minerals that are present on the moon, this scoop, 40 to 45% of the weight of that is oxygen atoms. So there is actually a lot of oxygen in all of the minerals that are present on the moon. The problem is more how do you get them out? But there is a lot. So you could almost do a 1-to-2 conversion in like the ideal case of the mass of minerals to the mass of oxygen you get out in the end.
Thank you. Since oxygen extraction seems a bit complicated, is there perhaps some form of plant or photosynthesis that can be used to produce oxygen?
Yes, that would fall in the category of when I was talking in the very beginning of the use of organic waste. Well, one thing you can do with organic waste is you can compost it, and then you can use it to grow plants. And I know there have been some studies on growing different plants in, for example, lunar conditions or in Martian conditions. This is something, in most cases, it is more looked at for the actual production of food, because even though it does produce oxygen by photosynthesis, it could produce enough oxygen, say, for the astronauts to breathe. But if you need the quantities of oxygen required to fuel a rocket, for example, you're going to need much greater amounts. So there you will need to have other sources of oxygen. But plants are a great source of oxygen. Yes, the extraction from the minerals is complicated. So another great source of oxygen is water. So if you find water ice, you can directly split it into oxygen and hydrogen, which is a pretty simple process. So if you manage to locate and extract or excavate water ice, then that's also an avenue to produce oxygen without needing to process minerals.
All good, thank you. Are there any other questions from the audience? You can type your question in the chat or just raise your voice. We have another one. Where geographically does ilmenite occur on the moon?
Excellent question. I actually have a slide for that. Basically, this is the answer. So this is a map that was made by the Clementine instrument. So it's an instrument that's on a satellite around the moon that measures the abundance of titanium on the lunar surface, or titanium oxide. And basically, this titanium in most cases is in ilmenite. So this is a pretty accurate mapping of where you find the ilmenite. And first of all, we can see it's not everywhere. So you do need, this is why I was talking about prospecting. It is important to measure ahead of time where you want to go, depending on the resource you're targeting. So if you are targeting ilmenite, well, you can see that this equatorial region is one of the best regions to go. And the reason for that, if I look just at the picture of the moon, 1 second, let's take this picture here. If we look at the picture of the moon, actually those high concentrations of ilmenite, they kind of correlate with the dark spots that you see on the lunar surface. And those dark spots are remnants of volcanic activity on the moon. It's actually, you know how on Earth, when you have volcanic rocks, they are dark because they're basaltic. Well, that's actually why you have dark spots on the moon, is because you had areas where you had volcanism, and this is the areas where the ilmenite seems to be more concentrated. Whereas in the lighter parts, we don't have that much ilmenite.
Okay. We have 2 more questions, and I think 3 more questions. So we have 4 more questions. So we need to be very quick on the answers to wrap up on time.
Yes.
So
Yes.
I'll start with the first one. Has 5 questions actually. So yeah, we'll see where we go.
Yes.
Has ilmenite other possibilities in terms of usage?
Well, I guess the simple one is if you're going to go through the trouble of extracting the oxygen, the next step is looking at the other products of the ilmenite, which are iron and titanium. So the short answer is yes. While you extract the oxygen, you also get as a bonus iron and titanium that you could use to, for example, manufacture metallic parts.
Okay, the next one is other than ilmenite, which other abundant ore slash material can be used for oxygen production?
Okay, so for oxygen production, the short answer is most, if not all, the minerals that you find on the moon are some form of oxide. So here, ilmenite, it's an oxide of iron and titanium, but you could also have an orthosite that I was mentioning, which is an oxide of aluminium, silicon, and calcium. So all of those contain oxygen. They are not all equally easy to break apart. So ilmenite is one we're looking at because not because it's the most abundant, but because it's one of the easiest one to split. So this process, using the hydrogen, for example, if you were to do this on something that contains silicon oxide instead of iron and titanium oxide, it would not work. You need more aggressive processes. But yes, you can find oxygen in all the other minerals as well. You just need different processes to access it.
Thank you. What are crucial technologies in the ISRU value chain that we are still missing? What's the missing link beyond the cheap regular access to the moon?
Yes, so cheap regular access to the moon, actually, maybe not cheap, but regular access to the moon is something we're slowly getting to. If you look at the news, year by year, there's more and more missions or attempted missions to the lunar surface. Regarding this value chain, I think we have elements in all of them. It's mostly about actually implementing those on the moon now. So, for example, prospecting, well, we have those maps that I showed you that give you kind of a course estimate across the whole surface. But what's really need to complement that is actually having more measurements on the surface with rovers or with actual astronauts going there. And it's kind of the same story for all of those boxes is we do have parts of it, extraction. We know different processes that work in the lab. Now we need to implement them on the moon and show that it actually works on the moon. So I think the key next step is taking all of those things and demonstrate them on the moon at a small scale first, and then eventually link it together to have an actual production, but already demonstrate the small boxes on the moon.
The next question is, will there be any limits to how long we can use oxygen extracted from the moon?
I mean, I guess the question is, are we going to run out of oxygen to extract? That is a valid concern because one thing we don't want to do is go at the moon in the same way as we go at Earth, which is just wildly extracting everything and then ask questions later. One of the saving grace, I would say for now, we're not looking at building cities on the moon anytime soon. Well, what is already an ambitious outlook for the next 10, 20, 30 years is having those kind of research outposts. So those are like you have a research outpost in Antarctica. So all things considered, it's very, very localized and very small piece of infrastructure, significant, but still very small. So at that kind of scale, no, you will have plenty of resources available. The one thing you could run out of, where you need to be a bit more concerned, because minerals, you find them basically everywhere. You find different minerals, you need to adapt, but you have valuable resources everywhere. One thing that is much more limited is when you start talking about water ice. So just for the quick story, water ice is only present in specific craters at the North Pole and South Pole of the Moon. And so you do have a very limited resource there. It's still a lot in terms of if you just have one astronaut drinking a glass of water a day, you're not going to use it up. But you have more concerns about you need to control that you don't just use everything up.
Okay, and the last question is, what is the most promising region or location to find iced water? Pole craters like Shackleton crater or buried underground?
So for the Moon, the current leading lead is craters, because we know that at the South Pole and North Pole of the Moon, if you have a crater, you basically have an area where you never have light, because the sunlight is basically horizontal, so it never reaches the bottom of the crater. And that creates what's called a permanently shadowed region. So it's a region that is extremely cold because it never gets heated up. And so this is where you can trap water ice. That's kind of where the water ice, you can only find it there. On the ground, I'm less certain. I think the water will mostly be just those permanently shadowed regions. But the underground question raises an important point, is that a lot of the data we have available for the Moon is just scratching the surface. It's just, well, all the remote sensing, it just tells us what's exactly on the surface and not what's underneath it. So to have more precision on what's underneath, we just need more missions that go there and drill deeper to see what you can actually get to underneath.
Very good and very interesting questions from the audience, I must say.
Yes, definitely.
Yeah. Okay, so I think we'll wrap up now. Thank you very much, Timon, for your insightful presentation and for sharing your experience with us today. Of course, thank you to all of you who joined the first session of the Summer Space Academy. We hope you enjoyed it and that you learned something new about the space sector. Before we close, just a quick reminder that our next webinar will take place next Thursday. My colleague Jordan will share the Eventbrite link in the chat so you can register directly. The next session will be hosted by Austria, and the topic will be Mars exploration in 3D. It's going to be a fascinating look at how we can explore the red planet using advanced imaging technologies. So once again, thank you all for being here today. We look forward to seeing you next week, and have a great day. Bye-bye.
Thanks, everyone. Goodbye.
Bye.